Hey, good morning, class, and welcome to lesson 5.1.3. What's up with E? The objective is I will learn about the number E and its application. Please take some time, look on your calculator. You'll see a little So this is something that's going to be on your calculator, something we're going to work with. It's just another base. And we're going to talk about where this letter E comes from. Help. A scientist has discovered a strain of extremely aggressive bacteria. Currently, the bacteria cover 1 centimeter square of a petri dish, and the scientist knows that the bacteria are reproducing at a rate of 100% every day. This means that after 1 day, the bacteria in the original 1 centimeter square will have produced another 1 centimeter square of bacteria, for a total of 2 centimeters square of bacteria. But in the meantime, new bacteria have been produced. These new bacteria will produce even more bacteria. The scientist is worried that at this rate, the bacteria will take over their lab in 1 week. Should the scientist be worried? Complete the parts below to help the scientist decide. The bacteria doubles in size in a 24-hour period, but the new bacteria are generated every hour. This means that after 1 hour, there's 1 and 1/24 centimeter squared of bacteria. Explain where the 1/24 comes from. Then, letting T represent the time in days, write an equation for the area. Well, that 1/24 comes from this type of idea. You have 100% of your bacteria right now. Now, if you divide that by 100 to get a non-percentage decimal, that's 1. That's where this 1 comes from. Then you're going to get another 100% of the bacteria over a 24-hour period. So let's first divide that by 100 to get 1, and then that's for a full day. But we want it per hour. So we have to divide that by 24 hours. So now you have 1 plus 1/24, and that's going to give you the 1 and 1/24. So your equation is going to be f of t equaling, you're starting out with this initial value of 1 square centimeter times a growth factor of 1 and 1/24 raised to the 24t, where t equals the number of days, and then f of t is the number of bacteria. Now we can take this and simplify it using our properties from a previous lesson. If I have 1 and 1/24, I'm going to raise that to the 24th power. Here's the power of the power property raised to the t. Well, 1 and 1/24 raised to the 24th power becomes 2.664 to the t. So that's if we're going to be compounding every hour. And now, what if instead the new bacteria are generated every minute? So let's convert 24 hours to minutes by multiplying by 60, and we end up with 1,440 minutes. Now we also want to do that every second. So now we got to take minutes and multiply by 60 again, and we will have 86,400 seconds. My equation then becomes y equaling let's use f of t. I'm just going to leave that 1 out in front, out of the picture. 1 plus 1 over 1,440 raised to the 1,440 times t, because that's the number of minutes in a day, and the 1 over 1,100, the 1 over 1,440 again comes from what we did before, where in one day there was 24 hours, so we had 1 and 1/24th. Here we're going to have 1 and 1/1440th. Then you have to raise your power to 1,440t. If I simplify this, 1 and 1,440th raised to the 1,440 power, all that raised to the t, I get 2.717 raised to the t. Now I'm noticing as we compound, this base keeps getting larger and larger. So let's see what happens if we compound every second of the day. So now f of t is going to equal 1 and 1 over 86,400 raised to the 86,400 times t, which I'm going to take 1 and 1 over 86,400 raised to the 86,400 raised to the t, and that becomes 2.718. Where it's this part right here. If I type that in my calculator, I'm going to get 2.718 raised to the t. But what if we do it every millisecond? So now a millisecond, that means that's every 1,000th of a second. So I'm going to take, on the previous page, 86,400 seconds per day times 1,000. I get 86,400,000 milliseconds per day. So we're going to compound 86,400 times. That equation, f of t, is going to equal 1 and 1 over 86,400,000 raised to the 86,400,000 t. Now I'm going to do all of this in just one step. I'm going to take and raise 1 and 1 over 86,400,000. I'm going to raise that to the 86,400,000. And so f of t equals 2.718 raised to the t. Now it doesn't look like this has gotten any bigger than when we compounded 86,400. So let's take this equation, f of t equaling 2.718 raised to the t. This represents after t days we will have F of T number of bacteria. Where we're literally compounding $86,400,000 times. Well, compounding that often, compounding every 1,000th of a second, is pretty much compounding continuously. So we're going to use this equation to calculate how many bacteria are at the end of 1 week. 1 week is 7 days, so we're going to take 2.718. We're going to raise that to the 7th power, and then, and I shouldn't say number of bacteria, it's the number of centimeters squared of bacteria. We will end up with 1,095 centimeters square of bacteria. So that's not a ton of area. I don't think that's going to encompass an entire lab. So we can conclude that the lab is safe, even though there is quite a few square centimeters of bacteria. Now, what we're going to do is we're going to take a look at that base. That base was 2.718. I would like you to go to your calculator and find the LN button. And the second function of this LN button is your E to the X button. So I would like you to type in, here's the keystrokes, go second, which is the blue button in the upper left corner, LN, and what you'll see on your screen is E. And I want you to raise that to the 1 power, and then hit enter. And what you should get on your screen is a decimal of 2.71828, so on and so forth. So this is what we call compounding continuously, and it is the same value as this E. And so E was developed by mathematicians to represent things that occur naturally in our world. When you talk about growth of a tree, when you talk about growth of population growth, when you talk about growth of bacteria, and that's just to name a few things that grow continuously. Because if you think about population growth, do you have exponential population growth where all the babies are born on 1 day per month, and so you're compounding 12 times per month? No. Babies are born continuously. They're born in the morning, they're born at night, they're born every day of the month, every day of the year. So we want to use this function of y equaling e to the x to represent things that grow exponentially at a continuous rate. So let's take and build a table on your calculator. So you're going to go to y1, type in e raised to the x, and let's go from x being a negative 1, 0, 1, 2, 3. So e to the negative 1 is 0.3679. I'm going to go just 0.368. Anything to the 0 power is 1. We know e to the first power is 2.718. E to the second power is 7.390. And e cubed is 20.0 8, 6. So if I plot those points over here, a -1, and then up 0.3, 7, 368, 0, 1, 1, 2.718 is right in there, 2, 7.39, and then 3 is going to take me off the board. Here's my exponential curve for y equaling e to the x, and don't forget there is this horizontal asymptote on the x-axis. In closing, what we'd like you to do is apply some transformation skills to this new curve. So if you are given e to the x as your graph, what does that look like under a transformation of f of x minus 2? What does that look like under a transformation of 2 times f of x? What I'd like you to do is pause this lesson and then take your table, build a table or copy the table from the previous page onto this page, and you can also copy your graphs if you would like to from the previous page onto this page, and then apply a transformation of f of x minus 2. Apply a transformation of 2 times f of x, and then check your work. So pause this and then come back. Okay, welcome back. In this first one, your graph is going to be shifted 2 units to the right. So here is the table from the previous page, and if I'm going to be shifting it 2 to the right, the x has 2 added to it. So a -1 plus 2 is 1, 0 plus 2 is 2, and we have 3, 4, 5. Plot these points, and that's what you will see right here. And here's your graph, excuse me, of y equaling e raised to the x minus 2 with the horizontal asymptote on the x-axis. In the second one, 2 times f of x, that's going to be stretched vertically by a factor of 2. That means all of the output values become twice as big. So I'm going to take this column in my table and double it and plot those points. As you can see, I've done that here. And here is the graph of y equaling 2 times e to the x. Hopefully you found this video informative, useful. Please, students, make sure you're getting those exit slips done. The participation for homework, I think, is slowly improving. Exit slips is still a little bit more of a hit or miss. The concepts in the exit slips do represent essential skills, test questions, and concepts from your lessons. So good luck. Have yourself a great week, and we will talk to you tomorrow.